Have you ever wondered how massive ships, some weighing thousands of tons, can float on water? The answer lies in a fascinating principle discovered over 2,000 years ago by a Greek mathematician and inventor named Archimedes. Legend has it that Archimedes was taking a bath when he noticed the water level rising as he lowered himself into the tub. This simple observation sparked a groundbreaking realization. An object submerged in a fluid experiences an upward force or buoyancy equal to the weight of the fluid it displaces. This became known as Archimedes' principle, a fundamental law of physics that explains why ships float. When a ship enters the water, it displaces a large volume of water. If the weight of the displaced water is equal to or greater than the weight of the ship floats. This principle applies to any object submerged in a fluid, whether it's a giant cruise ship or a tiny rubber duck. Buoyancy is the upward force exerted by a fluid that opposes the weight of an immersed object. Imagine holding a beach ball underwater. You can feel the water pushing back up against your hand, trying to force the ball back to the surface. That upward push is buoyancy. Buoyancy is caused by the difference in pressure between the top and bottom of the submerged object. Pressure in a fluid increases with depth. Therefore, the pressure at the bottom of the object is greater than the pressure at the top. This pressure difference creates a net upward force, buoyancy, that acts against gravity. Water, like all fluids, exerts pressure. Pressure is the force exerted over a given area. As you go deeper underwater, the pressure increases. This is because the weight of the water above you also increases with depth. Imagine a stack of pillows. The pillow at the bottom of the stack feels more pressure than the pillow at the top because it's supporting the weight of all the pillows above it. Water pressure works similarly. The deeper you go, the more water there is above you, and the greater the pressure. This increase in pressure with depth is crucial for understanding buoyancy. The greater the depth, the larger the pressure difference between the top and bottom of a submerged object, and therefore, the greater the buoyant force. Whether an object floats or sinks depends on the balance between its weight and the buoyant force acting upon it. If the object's weight is less than the buoyant force, the weight of the fluid it displaces, the object will float. If the object's weight is greater than the buoyant force, it will sink. Think of a hot air balloon. A hot air balloon rises because the hot air inside is less dense than the cooler air outside. The buoyant force acting on the balloon is greater than its weight, causing it to float upwards. Conversely, a rock sinks because its weight is greater than the buoyant force of the water it displaces. Section 5. Shape matters. How ships are designed to float. The shape and design of a ship play a crucial role in its ability to float. Ships are designed to displace a large volume of water, maximizing the buoyant force acting upon them. Their hulls are typically wide and hollow, allowing them to displace a large amount of water despite their weight. The shape of the hull also affects the ship's stability. A wider hull provides greater stability, while a narrower hull reduces drag and allows for greater speed. Shipbuilders carefully consider these factors when designing a ship for its intended purpose. Section 6. Cargo ships and submarines. Buoyancy in action. Cargo ships are a prime example of buoyancy in action. These massive vessels are designed to carry immense loads of cargo across the world's oceans. To accommodate the weight of the cargo ships have large, spacious hulls that allow them to displace a massive amount of water. Submarines, on the other hand, are designed to control their buoyancy to submerge and resurface at will. They have ballast tanks that can be filled with water or air. To submerge, the tanks are filled with water, increasing the submarine's overall density and causing it to sink. To resurface, compressed air is pumped into the tanks, forcing the water out and decreasing the submarine's density, allowing it to float back up to the surface. Section 7. Simple experiments. See buoyancy in your kitchen sink. You can demonstrate the principles of buoyancy with simple experiments at home. Fill a sink or basin with water. Take a small, dense object like a rock and place it in the water. Observe how it sinks to the bottom. Now take a less dense object like a cork or a piece of wood and place it in the water. Notice how it floats effortlessly on the surface. You can also demonstrate the impact of shape on buoyancy. Take a piece of aluminum foil and form it into a tight ball. Place it in the water and it will likely sink. Now, unfold the same piece of foil and shape it into a boat-like structure with high sides. Place it gently on the water's surface and you'll see that it floats. This demonstrates how the shape of an object can significantly impact its buoyancy, even if its weight remains the same. Section 8. Buoyancy, the unsung hero of the seas. Buoyancy is an essential concept in maritime engineering and naval architecture. Understanding buoyancy is crucial for designing ships, submarines, and other marine vessels that can safely and efficiently navigate the world's waterways. From giant cargo ships transporting goods across vast oceans to sleek sailboats gliding through the water, buoyancy plays a fundamental role in their ability to stay afloat. Section 9. Conclusion: floating into the future. The principles of buoyancy, first understood by Archimedes over 2 millennia ago, continue to shape our world today. From the massive cargo ships that transport goods across the globe, to the sophisticated submarines that explore the ocean depths, buoyancy is the invisible force that makes it all possible. As we venture further into the future, our understanding and application of buoyancy will undoubtedly continue to evolve, leading to even more innovative and awe-inspiring feats of maritime engineering.